The cross product of two vectors is another vector in this case. And it equals, I have a good chance of getting this backwards now, y1 z2 minus c1 y2 is the x coordinate of it. C1 x2 minus c2 x1, x1 y2 minus x2 y1. Those are the x, y, and z components. You notice that the x component has y's and z's in it, y component has x's and z's, and the z component has x's and y's. The interesting geometric thing about the cross product, I have the old blackboard erasure problem here. At least to start out with, things are simple enough that I might not even be writing this down. Cross product is interesting in that take the two vectors. The cross product is a vector which is perpendicular to both of them. And the length of it is equal to the length of P1 times the length of P2 times the sine of the angle alpha between the two. This means that if the sine of alpha is equal to 0, and that is if the angle between these is 0, then the cross product is 0. So a vector across with itself is a zero-length vector, various things like that. There's a shorthand notation for cross product, which is useful to know because it generalizes to some other things. If you write the two vectors in question as two rows of a kind of pseudo matrix and write the top row of the matrix with little symbols I, J, and K, thinking of I, J, and K as being unit vectors in the final x, y, and z direction, then by taking the determinant of this matrix, you come up with this same expression here. It's y1 z2 minus y2 z1 times the unit vector I in the x direction, plus etc. So this is a way of making sure you get the sign to come out right, because it's easy to get the sign reversed. Dot product is commutative. Cross product is not. Cross product of x2 times 0.2 times 0.1 is minus the cross product of 0.1 times 0.2. So if you do them in the wrong order, you're going to get the sign flipped. The mention of the word determinant here reminds us that I haven't officially stated what that is. Matrices. Matrices are generally rows and columns of numbers that stand for something or other geometrically. The determinant of a matrix is sort of recursively defined. And we can start out with a special case, just definition of the determinant of, say, a 2 by 2 matrix is the product of these two elements across this diagonal minus the product of those two elements across that diagonal. The determinant of a bigger matrix is defined in terms of smaller matrices by saying, we'll start out with the top row, and it's going to be A times the determinant of what's left of the matrix if you erase all the rows and columns containing A, which is E, F, H, and I, minus B times the determinant of what's left if you erase the rows and columns containing B, which is D, F, G, and I, plus C times the determinant of what's left when you erase those, D, E, G, H. So this is a definition of the determinant for a 3 by 3 matrix. It's in terms of these three 2 by 2 matrices, which you plug it into this formula to find out. The trick here is that you take A times this thing, minus B times its thing, plus C times this thing. You alternate the signs going across the top row. If you play around with the mathematics of it, you get essentially the same thing if you were to take the bottom row and take G times what's left if you remove it, minus H times what's left if you remove it, plus I times what's left if you remove that. And in fact, for a 3 by 3 matrix, there is another shorthand notation for this. It's the product of this thing, AEI, plus the product of BF, and you kind of wrap around here and pick up G, plus the product of C, and you wrap around there and you pick up D and H. So it's plus the product of all the things going down in that direction, minus the product of all the analogous things going up in this direction, minus GEC, minus HFA, minus IBD. 3x3 matrices are interesting. 4x4 matrices are even more interesting, and we'll deal a lot with them. There's no real simple trick like this for a 4x4 matrix. You have to do it by taking the submatrices and shaving off rows and columns and so forth. But it builds up. Now, when you have two matrices, typically we'll be dealing with square matrices here, 3x3 or 4x4 usually. One other interesting thing is to find the inverse of that matrix. Presuming you know what matrix multiplication is, the inverse of the matrix A here, sometimes written A to the minus 1, is whatever matrix it takes to come up with the identity matrix when you multiply them together. And various mechanisms for figuring out the inverse matrix, but the inverse matrix does not always exist. What you're effectively doing here is matrix division. This is kind of 1 over A here. And just in the case of scalar division, an inverse of a number doesn't exist if that number happens to be 0. And for certain types of matrices, called singular matrices, there does not exist an inverse of that because it is in some sense 0. And the it, in this case, is the determinant of the matrix. That's the flag that tells you if the inverse exists. It's sort of like trying to divide by 0. How do you come up with the inverse of a matrix when somebody hands you one? The inverse is defined in a recursive manner very similar to what we just did for determinants here. There's a particularly simple formula for all matrices, which kind of devolves into something trivial for the 2x2 matrix. I'll just tell you what it is for 2x2, and then we'll kind of see how it fits into the general scheme later. It's D minus B minus C A times 1 over the determinant of the original matrix. If we try to multiply these things just together by this, forgetting we won't divide yet, we come up with AD minus BC, and then we come up with minus AB plus AB, so that's 0, and we come up with CD minus CD, so that's 0, and minus BC plus AD there. This is almost the identity matrix, except for the fact that instead of 1s along the diagonal, we got AD minus BC, which is the determinant of this original matrix. So that's why we have to divide by it. Now, if we want to generalize this to the, say, 3x3 case, we wind up with the following thing. First of all, you do kind of an analogous thing to what I just did here for flipping around the numbers. What you do is you take each element of the matrix and you replace it with the determinant of the 2x2 matrix left over if you erase that row and column. So you replace A with the determinant of EFHI, replace B with the determinant of DFGI, replace C with the determinant of DEGH, replace D with the determinant of BCHI, etc., etc. So you get 9 of these numbers. Similar to what we were doing in order to take determinants in the first place, right? You have to take all these little sub 2x2 determinants here. First of all, come up with this thing. Then you go through and in sort of a checkerboard fashion, you flip the signs of every other element. In this case, if there's only 3x3, it's those 4 that have the negative in front of them. This is similar to the thing that we did with the determinant, where we had to have A times something minus B times something, back where I erased it. So anything in these kind of checkerboard cells usually gets its sign flipped. So 1, determinant matrix. 2, flip signs. 3, transpose matrix. That is, you reflect the elements around the diagonal. You interchange anything that's across here. So you flip these two, you flip these two, anything on the diagonal kind of flips with itself so it doesn't move, and you flip these two. You exchange those values. And then 4, you divide by the determinant. Whew. Okay. This is essentially what we did for the 2 by 2 matrix. The same thing, only it was so trivial to do that because take A and replace it by the determinant of what's left if you erase the rows and columns. Well, that's just D, so we plugged in a D here. Take B and replace it by the determinant of what's left when you replace it, when you erase it, which would put a C up here. Take C and replace it with B, and take D and replace it with A. Flip the signs, and then transpose the matrix. So that's why we got B up here and C down here. And so the 2 by 2 case is just a special case of what I just did. For a 4 by 4 matrix, you have to come up with 16 3 by 3 determinants, which is a bunch of 2 by 2 determinants. Things get messy. 16 by 16 matrices, you start getting into writing a computer program for it. However, I have found that I wind up doing symbolic matrix inversion a lot in terms of working out certain geometric problems. And so this is something that if you do this very much, you're going to wind up doing more than once. Okay, that's basic linear algebra. Okay, next thing is how do we represent the geometry of a situation we're going to draw a picture of? Generally in computer graphics you use what are called homogeneous coordinates, which is a slightly different way of doing things than what you'd call standard Euclidean geometry. It has certain advantages in terms of efficiency and convenience for particular types of geometric operations. The first thing you have to realize is that each point in 3 dimensions is represented with 4 numbers instead of 3. Call them x, y, z, and w. This 4th number here seems a little bit spurious. Typically that number will be equal to 1. But in general, what the generalization is here is that once you come up with a set of 4 numbers that represents a particular 3-space point, you can multiply all those 4 numbers by the same value, and it will still stand for the same point. So it's sort of a redundant notation here. As long as this number is not 0, if you multiply them by 0, all bets are off. You've got junk left. But typically, you can multiply it by anything you want to, and it still represents the same point, the way all the interpretation of the algebra works. Now, if you want to find out where the point really is, which is sometimes interesting, you typically multiply by 1 over w. That is, you divide by w, which forces this last element here to be equal to 1, and then the first 3 components are the genuine x, y, z coordinates of things. So a point is represented by this 4-element vector. In mathematics, generally vectors or points are drawn as columns of numbers. In computer graphics, we draw them as rows of numbers. Most of the mathematics that has come to be traditional in computer graphics is the direct opposite of what mathematicians generally do. We always use left-handed coordinate systems and row vectors and bunches of other things. There's a branch of geometry called projective geometry, which also deals in homogeneous coordinates, and they typically put the w as the first element instead of the last element. If you're talking to a mathematician, expect to be confused a little bit. Transformations. Once we got this cloud of points defining some object, we'd like to be able to do some simple geometric operations on it. Kind of 3 basic transformations are rotations, translations, and scaling. Each of these has a kind of a canonical matrix which stands for what it does. Do the last 2 first. standard translation matrix is this 4 by 4 thing, x, y, z in the bottom. Everything else kind of looks like an identity matrix. So if you were to take, used up x, y, z as members, let's say x prime, y prime, z prime, and 1. This is a standard, some random point that we're going to plug into here. You multiply this and you get out, not too astoundingly, x prime plus x, and y prime plus y, and z prime plus z, and 1 again. So you're essentially just adding this constant x, y, z displacement to everything that you multiply by this matrix. Scaling looks like that. It looks like your stuff on the diagonal, the x, y, and z scale factor, which can all be the same if you like, along the diagonal. And so multiply that by our test point here, x prime, y prime, and z prime. You come up with x prime sx, comma y prime sy, comma z prime sz, and 1, so forth. Scaling and translation are trivial. One thing to remember about this is that the matrices also have this property that any non-zero scalar multiple times the matrix represents the same transformation, just like we did with points. We can multiply all these numbers in here by 10,000 or by 0.02, multiply all 16 of them, and it still represents the same thing when you plug it through here, because kind of when you multiply the vector times the matrix, the product is indistinguishable from where it came from the vector or from the matrix. This is useful in, say, making hardware to do these transformations, in that it allows you to use integer arithmetic a lot of places where you might not ordinarily think so. In that you can make all of your transformation matrices be scaled integers, and if the numbers you want to put in here really are like 0.5 and 0.2 or something like that, just scale a whole matrix by 10, and you have 5 and 2 and 0 and 10. They're all integers again. So you're sort of inherently doing what you might call a rational arithmetic sort of thing. You're representing numbers, floating point numbers, as the ratio of two integers. There's always this dividing by the w that's going to happen sooner or later in order to turn it back into the real world space. Rotations. Various interesting things to say about rotations. They're a little bit more elaborate than translation and scaling. To start out with, typically think of the 3 standard rotations around the different coordinate axes. Where S and C represent the sine and the cosine of the angle that we want to rotate by. And the appropriate y and z matrices are sort of simple permutations of this. I'll just write them down. You notice the order I'm writing these down, this little mnemonic for keeping track of what goes where. Cosines are always on the diagonal, step 1. The vector you want to rotate around always has the unit kind of vector along it. Since it's x, the first row and the first column have the 1s and 0s in it, and always the fourth row and the fourth column have 1s and 0s in it. So whatever's left is where the cosines and sines go.
I believe that's cosine minus sine, and sine and positive sign for x, isn't it?
What's that, huh?
Long sign on the sines. Long sign on the sines.
Okay, I'll get to that in a minute. That's the one that's backwards. Okay. This is a C, and that is a C, and this is a C, and this is a C. A little bit smeary here. Okay. Just putting them up there now to explain what the trick is. Like I say, cosines are always on the diagonal. The sines go kind of in the opposite corners of where the cosines went. In this case, of y, it's the second row and column that's the unit thing. In this case, for z, it's the third row and column that's the unit thing. Now, a question about the algebraic sign of the trigonometric sine function here. I put the minuses here, here, and here. There is no firm standard convention as to which direction is positive rotation on this thing, but there are a few good ideas, and this is it. If we imagine an XYZ coordinate space, this is a negative, left-handed coordinate system here. So x goes kind of this way and y goes like that. It makes z go into the screen when you're looking in the standard XY sort of thing. A left-handed coordinate system, what we use is what's called the left-hand rule for which direction is positive, which means you stick the thumb of your left hand in the direction of the axis you're rotating around, and your fingers curl in the direction indicating positive rotation. And if I haven't blown it too bad, that should be the case for here. If we take just the unit vector along the x direction, 1, 1, 0, 0, 0, 1, multiply by this, we get cosine and sine and 0 and 1. So that for some small angle, we have taken the x-axis and rotated it up like that. So that works out right. Yeah. Okay. We have the left-handed coordinate system with a left-hand rule. Now, if you want to use the right-handed coordinate system, you use the right-hand rule. And if you plug it in, you discover they're exactly the same matrices. So it makes no difference what the matrix is. It just makes a difference whether the handedness of the coordinate system and the handedness of the rule match up or not.
So the reason we use it is we want Z to go in and not out.
That's the historical precedent for it, yes. It's a bit of a nuisance, and in a certain sense, it doesn't matter because in a minute I'll get to how you can flip back and forth without hopefully getting too confused.
And you're defining your rotation clockwise or counterclockwise?
Well, depends on which direction you're looking from. If you look in this direction, it goes counterclockwise, and if you're looking in this direction, it goes clockwise, right? So that's why you have to use the handedness of the rule, because that's a fairly unambiguous, thing. The thumb points in the, the direction that the axis does.
Well, the reason I ask is this is the opposite convention as in Newman and Sproul.
Well,
No?
yeah, I'm a little bit surprised at that, but like I say, there's no standard convention of this thing. This is the one that I have found. I unfortunately have two programming systems that do it two different ways myself, so I have to keep track of. I'll tell you one thing about computer graphics. We'll sit and argue about this. We'll say this is the way it'll be, and there are various other things we talk about, like where you define points clockwise or counterclockwise around polygons when you're defining a data structure. And this determines whether the thing is positive or negative sign, whether it's facing you or not. You'll think about these things, and you write the program, and you still only have a 50% chance of it working right. And so if it's wrong, you go in there and you flip the sign in the code, and you say, now I know why it's working, and you don't think about it too much. This always happens. It's nice because it's obviously going to work or not. You just run some test cases through and see if it's right, rotating in the direction that you like, and if not, all it is flipping the sign, right? Again, in the sign, you either pick one or the other, but you should at least make them consistent here. And that's why I was careful to put the minus signs where I did here on those. A mnemonic for that is that the minus signs always go in those positions, forming a little triangle pointing in the upper right, since it's a left-handed coordinate system. So if a sign falls in one of these three locations, then you know it has a minus in front of it. Otherwise, the x and y's rotate in different directions than the z's, which is obviously no good. Some other interesting properties of rotation matrices. Let's just take a look at the upper left 3 by 3 thing. That's just the pure rotation. The inverse of a rotation matrix is equal to the transpose of the matrix. Very simple to invert rotation matrix. You just flip them around the diagonal. And if you don't believe that, homework assignment number 1 is to prove that to yourself. Now, typically you won't do just one rotation or one translation or one scaling on things. You will do a whole bunch of them to position it here, make it bigger, rotate it, put it up here, make it smaller, and so forth. So you will be multiplying a bunch of these matrices together to get one big lump matrix that stands for the entire transformation from the definition space of your object to where you actually want it in the universe. So if you multiply a bunch of rotation matrices together, you'll get a set of 9 numbers. Now, if you know you started out with rotation matrices, then there are a few special properties of these 9 numbers. Just any random 9 numbers off the street doesn't qualify as a rotation matrix. In particular, it has to satisfy this and satisfy a few things like things don't stretch and perpendicular lines remain perpendicular and so forth. And it so happens that any random product of rotation matrices can be expressed as one net rotation around some axis sticking out in some direction. Might not be along one of the coordinate axes, but it will be a rotation around some line. That is, for any rotation matrix, there is a line which none of the points on it move. They kind of rotate around themselves. Everything else kind of orbits around that line. Now, the question then is, if somebody hands you such a line and a angle, how might you construct the proper rotation matrix from this? Standard sample geometric problem. Somebody hands you the vector q, say, and says, just in terms of its coordinates, qx, qy, qz, and an angle, and says, make me a rotation matrix that rotates that many degrees around that axis. First of all, let's assume that the length of this matrix is, or the length of this axis is 1. If it's not 1, you find the length of it, dot product of it, square root of the dot product of it with itself is the length, and you divide it into all these things. So that gives you a unit length vector. Did Nelson talk about this? Yes. Shaking heads. Yes? Okay, I'll race through it very briefly here. Here's a sample point that we're going to rotate around Q. P prime is where the point rotates to as a result of going around whatever it is, theta degrees. So we want to find P prime in terms of P and Q, right? Step 1 is to project both P and P prime onto a plane perpendicular to Q. That is, we're kind of going to look down along the axis of Q. We're going to look down on top of it. So let's call this P hat and call the other one P prime hat. What is, let me see. Yeah. So what we're going to do is split P up into 2 parts. There's this part here, which is a projection along Q, and then there's the other part, which is the perpendicular to the projection along Q, right? Now, the part that rotates is just these projections here. The projection along Q doesn't change. So the projection of P onto Q and P prime onto Q are both the same. So at least that much of it we know already. It's Q times P dot Q. I'll put little arrows over the vectors here to make sure that we keep track of what's a vector and what's a scalar. P dot Q now is the dot product of these two things. It's the length of this times the length of this times the cosine of the angle in between. And since the length of Q is 1, that doesn't affect it, but the P dot Q will give basically the length of this projection here. Another geometric interpretation of the dot product. So this part of it is just that piece of vector there, right? Now if we take P prime along here, and let's make a top view, sorry, P hat, and let's invent another direct vector that's called R, which is perpendicular to this. This is kind of a little two-dimensional coordinate space now. And so the other two components of this thing are that. So this is the whole expression for P prime. This thing here is projection onto Q. These two components are the sine and the cosine of the amount that this thing is rotating around here. Okay. We still need to know what that and what that are. P hat is the projection onto here. That's kind of what's left over after you subtract off this thing from P. It's P minus that. P minus the projection out of Q, so you just kind of flatten it down into here. That's P hat. And I'll wave my hands a little bit and tell you, if you want to play around with it at home, R is equal to the cross product of Q and P hat, which is equal to the cross product of Q and P. So, put them all together, they spell that. This is sine. Well, this is just a long string of equations here. What we're interested in is a matrix, right? We want to turn this thing into something of the form, the vector P times some 3 by 3 thing. I actually slipped one by you here. I flipped the sign of the cross product. I can never remember which way those go. And oh, well, the cosine of theta. This is not the argument of the cosine. This is something that's multiplied by it. Sorry. This is the cosine of the angle, and this big smear here is the sine of the angle. Sorry. I write cosines and sines so many times that I usually just not bother to put the angle in there sometimes, because it's the cosine of whatever angle is interesting at the current time. So you'll have to keep me on my toes for that. What we want to do is kind of factor P out of each of these terms so that we can treat it as a matrix, right? Oh, vector, 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 vector. Vector. Is that what you're looking for? Sure, sure.
Why did you flip the Q and P?
I had it written down that way on this piece of paper, and I derived it differently.
So which is right? The top is the bottom?
The difference will be just which direction is positive and negative of rotation. That's the only difference it'll make. And I forget which one is right. You'd have, you know, it's the sort of thing that I'm only going to get it right half the time anyway, so why bother embarrassing myself by making a definitive statement? Certainly, and just kind of make it work when the program shows up. Okay, the first term here, we want to factor P out of this thing. Well, this is Q times some number here, so this is a vector. So it can be represented as the product of the vector P times something. What might that something be? Well, there's a few rabbits out of a hat coming along here. Term 1 is P times, let me write it the following way. P dot Q times P. Since this is a scalar that we're just multiplying, we can do it on the left or the right. Commutative, right? Get away with that. Oh, sorry. Q. P dot Q times Q. P is a row vector like this, right? Now, in order to take the dot product of it, you can think of it as a column vector. So this is Q. You can think of this one now as a row vector, Q, like that, and here's P. A lot of geometric interpretations of algebra here, folks. Let's now multiply these together in a different order. Let's multiply these two together first. Now we have P times the matrix. Now this is the reverse of what you typically think of in terms of taking a dot product. Another name for dot product is inner product, right? This thing is sometimes called the outer product. It's Q as a column times Q as a row, which means that it's a 3 by 3 matrix now. Qx squared, Qx, Qy, Qx, Qz, Qx, Qy, Qy squared, Qy, Qz. I even have a piece of paper which has this on it. It's called N here instead of Q, but to make that a quick translation, etc., etc. 3 by 3 matrix, which is this one here. Do you all have monitors? Are you seeing this on your monitors?
No.
So much for that. Yes. Oh, okay, goody. Thank you. So this is the thing that I just got done writing. It's called V in this case, and it's multiplied by 1 minus cosine of A. There's a little bit of factoring around here. This lump here and this lump here, you notice, are the same, and so what we did was to say cosine of angle times P plus 1 minus cosine of angle times lump. Right, and that's what that is. And the last thing here now, we want to factor a P out of the P cross Q thing. Another rabbit out of a hat in that if you know what P times P cross Q is, you can write it as the following matrix product. I'll just cheat and peek here. Q, just got to be X. Right? Yeah. All we've done is, something's fishy here, is that? No, that's right. All we've done is rearrange the elements of Q, the X, Y, and Z components of Q, or in the case of the piece of paper, N, and put them in here. And so if you notice, if you multiply this thing, P times this, you're going to get Y times QZ minus... Yeah, I thought there was something fishy there. Got X and Y backwards. Okay. Y times QZ minus Z times QY, etc. This is another way of writing the cross product. So again, this is just a little bit of algebraic skullduggery here in order to change this into the product of point times matrix. So as a result, you can multiply these or add these three matrices together. U times the sine, which is this thing I just wrote up here, plus V times 1 minus the cosine, plus the identity matrix, essentially times cosine of A. That's this term here. Gets an enormous god-awful mess, and it's the rotation matrix of points around any arbitrary vector in space. Well, that's interesting purely as a academic exercise, but it's also interesting in a couple of geometric situations as well. For one thing, it's good practice at dealing with what exactly is a dot product good for. Well, you can use it to find the projection of a vector on a plane perpendicular to another vector, things like that. And practice in what the cross product is and how you can represent the cross product in different ways, so forth. The other interesting thing is, suppose we want to take the opposite direction. Suppose somebody hands you a 3 by 3 matrix and promises you that this